things that you want to learn by the end of the hour. So let me make sure this is in focus because it's not. First of all, we want to know what is inertia and how does it relate to force, right? Inertia. How does it relate to force? Goal number 2, we want to be able to calculate force, mass, and acceleration. Be able to calculate force, mass, acceleration. And number 3, be able to identify what is meant by an action-reaction pair. Explain what an action-reaction pair is. So if by the end of the hour you can do all these things, you're going to be great for Friday's quiz.
By the end of the hour?
And then really the rest of the week, we're just working on these 3 things.
So when's the test?
End of next week at the earliest. It's not terribly long. All right, so start off. Let's see here. We want to define what a force is. A force in the book is some fancy definition with all sorts of unnecessary words. A force, in the most easy way to put it, is a push or a pull. A push or pull. Okay. All forces are measured in newtons when we're in the SI unit. Measured in newtons. And a newton is a derived unit. That means it's made up of other smaller units. But a newton, 1 newton, is equal to 1 kilogram meter per second squared. So a newton is equal to an acceleration and a mass multiplied together. Okay. English system for forces. What would you think the English unit for force is? Any guesses? That's mass. So in the English system, the unit for force is pounds. All right. So when we talk about forces, one of the things that we have to recognize is that forces are vector units. Since forces are vector units, what does that mean is important? And magnitude and direction are going to be important. So let's go ahead and give an example here of some forces. We've got a box, and a tier has decided to push the box. Okay, what forces are acting on the box? What pushes or pulls are acting on the box? All right, a tier. A tier is pushing the box. Force, a tier. Did I mix with them? Is IE or EI? There. Okay, we've got force of a tier. Anything else pushing or pulling on the box? Friction. Which way is friction going to be acting? Opposite way. Friction's not going to help you push it. It's going to hinder it. Force, I'm just going to write small f for friction. Is there anything else pushing or pulling on this box? Okay, I could have some air resistance. I might put that in here. Say again. Gravity. Force, gravity. All right, so I've got a tier pushing it forward, friction trying to hold it back, gravity pulling it down. Anything else? Yeah. I mean, unless you can somehow turn off basically every other object in the universe, Yeah, gravity's always going to be there. Okay? Even if we're talking like middle of space, gravity is definitely still there. Gravity is very there. All right. So next thing we're going to look at here then, net forces. A net force is the sum of all forces acting on an object. The sum of all forces acting on an object. So if I wanted to know the net force acting in the horizontal dimension, I would compare these two forces. Now, hopefully my drawing shows it, but a Tier's force in this case is stronger than friction. So the total net force is going to be some amount that way. Okay? However, if I look in the vertical direction, I've only got one force here, correct? So the net force should be down. Because the net force acting on this box is down, what should this box be doing? More than that. Going down. That doesn't seem reasonable. There's got to be a force acting up. So anytime an object is not moving, or rather I should say not accelerating in a specific direction, forces in that direction must be balanced. So there's a force acting up here, opposing gravity. We call that a force normal. A normal force is a force that exists perpendicular to the plane of contact between two surfaces. A force that exists perpendicular to the plane of contact between two surfaces. So like if this is the plane of contact, perpendicular is that way, makes a right angle. Right. Right. So like if you've got something flat, it goes up. If you've got something vertical, it goes this way or this way. Yeah, yeah. The plane of contact between the surfaces. All right. So this normal force is basically the force that prevents objects from falling through each other. So like if your computer sitting on your table didn't have a normal force acting on it, it would fall through the table and hit the floor. Okay? So the normal force exists to prevent objects from basically falling through each other. Okay? Let's see here. So we've written force normal here. Let's talk force gravity quick. We'll get to it in a second. Fn, force normal. Force of gravity. Gravitational force in all cases is calculated as force of gravity is equal to the object's mass times gravity. Mass. And anybody remember what the acceleration due to gravity is? A little higher. It is in the nines. Not quite. 9.8 meters per second squared if you were on the surface of Earth. That is the rate at which objects fall. So last week we said all objects accelerate towards the ground at the same rate. We'd indicated this when we'd took a piece of paper, set it on a book, and dropped the book, right? We talked about if you took two objects, a golf ball and a bowling ball, and dropped them both, which one would hit the ground first? The answer was both. They hit at the same time, not the bowling ball. That was a daily question. Originally, it was a daily question. Okay, we said they hit at the same time. So this is because the objects accelerate at the same rate, not because they have the same force of gravity. An object's mass helps determine its force of gravity. Its force of gravity can also be called its weight. I'm not going to say because some people haven't taken the test yet. Uh-huh. Okay, so that starts to deal with what we call air resistance and terminal velocity. For the purpose of this, we're not talking about things reaching a fast enough speed to deal with terminal velocity. We don't deal with air resistance in this class because the equations for air resistance are ugly and involve calculus. So we just deal with things that move slow. Okay. All right. So force of gravity, mass times gravity. This is also known as the weight. All objects accelerate towards the ground at the same rate. So that's normal force. That's gravitational force. Next up is friction. There are two types of friction. Type 1 is static friction. Static friction, which is friction that exists between two surfaces that are not moving relative to each other. Friction that exists between two surfaces not moving relative to each other. And then we have kinetic friction, which is going to be friction that does what? Yep. Friction that exists between two surfaces that are moving relative to each other. Friction that exists between two surfaces that are moving relative to each other. All right. A couple of things about both types of friction. Friction always acts opposite the direction of motion or attempted motion. Always acts opposite the direction of motion or attempted motion. And friction, regardless of type, is calculated as the force of friction is equal to mu, a coefficient of friction, times the normal force. And mu, this is really just the Greek letter mu, which is like a U with a nosebleed. It is basically the grippiness between two surfaces. Between two surfaces. What would be an example of a pair of surfaces that would have a low coefficient of friction? Yeah. Ice and a hockey puck, absolutely. That would have a low coefficient of friction because there's not a lot of friction there. What would be an example of a pair of objects that would have a high coefficient of friction? Sandpaper on wood. Shoes on cement. Okay, so high coefficient of friction, lots of friction is there. Low coefficient of friction, not a lot of friction is there. Good? Okay, so few example questions then. I want to know about the friction that exists between these two books. Okay, so just looking between the books, I'm going to start out, I'm going to push this book that way. I am pushing on it, no, it is not moving. What kind of friction exists? Which way is the static acting?
That's where it's
Should be acting opposite the direction of detected motion. So since I'm trying to push this book that way.
Oh, I thought you were pushing it up because your hand's like on the bottom of it.
No, it's on the side. So friction's going left.
Friction's going that way. Left for you guys. Okay? I am pushing the book. What kind of friction? Which way? Opposite direction of motion. If the book is moving that way, friction's got to be that way. Okay? All right. Let's see here.
Are we going from our view or your view?
I mean, if you just point that direction, it doesn't matter if it's RV or yours. Yeah. Because we both agree on that way. Okay? How about now? Which kind of friction?
Oh, kinetic.
Which way? Good.
Wait,
Okay.
what's the difference between that?
Static, I push, but the book doesn't move. Kinetic, I push and it does move. Direction didn't change. Okay. Next one. Which kind of friction exists between them? And which way is it acting?
Down. Are you trying to?
Which way is the top book trying to move?
Nowhere.
Nowhere. So which way is the opposite of nowhere?
Nowhere.
So which way is the friction? Non-existent. Okay. To answer, or look at it in a different way. So when the two books are just sitting on top of each other, we say there is no friction between them because nothing's trying to move the top book. Which is easier, walking on ice or standing on ice?
Standing.
Standing. Okay? If you don't agree with standing, go out during lunch and try to walk on some slick ice spot versus trying to stand on an ice spot. You'll notice standing still is way easier. Okay? Now, the reason that we can relate that to this answer here, if we try to walk on ice, we need friction to walk. Without it, we probably slip. However, if I stand still on ice versus standing still right here, do I know the difference? I mean, not really, not unless I'm trying to twist my feet or do something, right? But if I'm just standing perfectly still, you will not notice the difference between standing on ice or standing on plastic floor, because friction doesn't need to act one way or the other at any given point. So there doesn't need to be friction there. So unless this object is something to start pushing it or trying to get it to move one way or the other, there is no friction. If there was friction and you picked a direction, the book would have to start moving that way. So if there was friction and we said friction was acting that way, nothing's opposing it, so the book would start sliding that way. Right? So since there's nothing opposing it, there's no motion to oppose, there's no attempted motion to oppose, there's no friction. Okay? All right, one more. Which way is friction acting between the books?
Nowhere.
Which way is friction acting between the books? Two parts. Relative motion between the books. There was no kinetic friction because they weren't moving compared to each other. Okay? There's also no static friction because nothing was trying to get one to move versus the other. So because they weren't moving relative to each other and nothing was trying to move one relative to the other, there was again no friction between them in that case. Logan doesn't like that answer.
Well, I know it is. So there's no,
I didn't say you didn't get it. I said you don't like it.
I don't like it. So there's no friction if you don't do anything.
If you're just sitting there, unless something is trying to get you to move in one direction or the other, like if you sat on the floor and didn't move, yeah, friction wouldn't be acting on you one way or the other. But like the way you've got your feet on the ground right now, there's probably friction between them unless your foot is sitting vertically, because without friction, your foot would slide forward, like if you're sitting at an angle. So yeah, friction's there because your leg would try to push out a bit. But if you've got your legs sitting just vertically and your leg wouldn't push forward or back or one way or the other without friction, there isn't any friction there. All right, so we've got force normal, force gravity, force friction, force of tear. So the last thing we need to talk on this set is force net. A net force, as we defined right here, is the sum of all the forces acting on an object. So let's say a tear pushes with a force of 200 newtons. And the force of friction acts back with a force of 100 newtons. And we've got an object that has a mass of 200 kilograms. Okay? How much force is acting in the horizontal dimension on this box? What is the net force acting on this box? Say again? How much? Why 100? Good. All right, so it's important again that forces are vectors. And when we have objects that are a unit that's a vector, direction matters. And opposite directions can be picked out, recognizing that one is negative. Which one do you want to make negative? Sure. So negative 100. So the net force then is equal to 200 minus 100, or plus negative 100, same deal. So the net force is 100 newtons acting on this object. Newton's second law tells us that a net force is equal to the object's mass times acceleration. Newton's second law. No, we have not yet talked his first. F net equals mass times acceleration. I write a lot today. Okay? That means that I say that my net force of 100 is equal to my object's mass, 200 kilograms, times acceleration A. I divide both sides by 200, and I get 1/2 is equal to A. So my acceleration is 1/2 a meter per second squared. Because F equals ma, and I divide. Or how do I know the unit? Which question?
Wait, so the net is 100.
Yep.
And then mass is 200, but mass is the same. And you're dividing by 200 because you don't know what the acceleration is?
Yeah. Yeah. Good. Anybody else? This right here, 1/2 a meter per second squared is the acceleration. Okay. All right. Next question for you guys. Is it easier to make a object or a lighter object? Lighter. So that is what we call an object's inertia, or its mass. So we see an object in Newton's second law, ma, and really it's in his first law that he describes what that is. Yeah. Sure. So she asked about how to get to this acceleration. She said that we got that the net force was 100 newtons because we had 200 minus 100. Net force is the sum of all the forces acting on an object, so we had 200 minus 100. We get 100 here. Since we know that 100 is the net force, Newton's second says that equals ma. 200 is the mass. Divide both sides by 200. 100 over 200 is 1/2. A meter per second squared is the acceleration. In this scenario, Newton's first law. An object in motion stays in motion, and an object at rest stays at rest unless acted upon by an outside net force. Object in motion stays in motion, and an object at rest stays at rest unless acted upon by a net force. By a net force. All right, we're going to change up this scenario just a little bit. Still got our box, still have it here, pushing the box. FA, FF, FN, FG. But now the applied force is 100 newtons. Applied force is still 100 newtons. This is our net force. 0. So F net equals 0, which is equal to ma. What's the acceleration of this object? 0.
How's our
because we have 100 here and we have 100 back, and 100 minus 100 is 0. F here or here? Here? FF, force friction. Typically what we do then is we have one equation for horizontal and one equation for vertical. Treat them separately. Okay? Hang on, I've got more question here. Is this object moving?
No. Yes. Yeah. It's going forward. It's moving at a constant speed.
Say that again?
Moving at a constant.
It could be moving at a constant speed. All we know is that this object is not accelerating. So it could be stationary. Maybe it's not moving, but Atir's right. Maybe it's moving at a constant speed. So we don't have enough information to say what's going on. If you told me it was static friction, yeah, it would be stationary. If you told me that it was kinetic friction, no, it's moving. Okay? But without knowing that other piece of detail, we don't know if this is stationary or moving at a constant speed. All right. Maddie, you had a question? Oh, okay. All right. Questions on Newton's first law here. So this object in motion could still be in motion. We just can't change unless it gets that net force to influence it. Newton's first law is also known as the law of inertia. Where inertia is simply a measure of an object's mass. The more mass you have, the more inertia, meaning the less tendency to resist, or sorry, the less tendency to change your motion. The less mass you have, the more tendency you have to have your motion changed. All right. Questions up to this point? Somehow we are way ahead of it. All right, Newton's third law. Yep. Laws of motion, 3. Laws of a lot. We only learned, well, for his laws of motion, we learned 3. But there are other laws we talked about that he came up with. All right. Newton's third law is probably the one most people know, like right off the top of their heads. What's Newton's third law? You guys knew that one too? For every reaction, there's an equal and opposite reaction. Okay, you've probably heard it at some point. Whether or not you remembered it is a different scenario. So action, I throw this ball. What's the equal and opposite reaction? Comes back at me, it goes forward, it bounces, it's rolling. How is that equal or opposite to me throwing it? Thanks. Aiden, what were you going to say? Eventually it's stopping. So what would be opposite about it stopping moving compared to me throwing it?
It's going away from you.
It's going away from me? Okay. Hint, nothing is equal or opposite about that. Nothing is. So Newton's third law, for every action there's an opposite reaction, doesn't seem to be right. Let's change up the scenario just a little bit. I'm no longer sitting in the classroom. I'm floating in space. I'm floating in space, and I throw the ball. What happens? All right, Newton's first law is pretty good there. That seems pretty straightforward. The ball just goes, and unless an outside force acts on it, the ball keeps going. But Newton's third law, for every force or for every action, there's an equal and opposite reaction. still doesn't seem to.
So what are these laws?
How can this be a law if it doesn't seem to apply? Anybody seen the movie Gravity? That movie was amazing. Your opinions are wrong. It's so good. So, Sam is in space trying to solve the most dangerous environment known to man. Yeah, everything about space wants to kill you. It's cold. There's no oxygen. There's no gravity to bring you back down. Space is. See ya. So one of my favorite quotes, say is awful. Aim for the moon, even if you miss, you'll land in the right? That's the inspirational quote. No, aim for the moon, you better hit it. Because if you miss, you're going to die drifting, cold and alone, lost in space forever. So, yeah, space is the most dangerous environment known to man. He did enjoy that. I'm glad somebody appreciated it. So, Sandra Bullock, movie Gravity. How does she move around? Hang on. Yeah, she does not. She can't, there's nothing to swim against. She has to push off. Okay, she has to push off things. What else does she do when hey guys, what else does she do when she's inside those stations? She doesn't have one. For the very beginning of the movie, and then she does that. How does she move around? No. So she was able to, in the movie, change her direction or navigate because she would take, first of all, for a while she had a fire extinguisher and she used it as a thruster. And she would use the fire extinguisher and push it, point it in one direction, and she would get launched in the opposite direction. The other thing she'd do when the fire extinguisher ran out, what'd she do? People who saw the movie. Anybody got an idea as to what she could do? Yeah, no, because she was inside her. Yeah. She could have pushed off with the fire extinguisher. She could have thrown the fire extinguisher. She did. So when she throws the fire extinguisher goes one way, she goes the other way. So when we're talking about this ball and this equal and opposite reactions, when I throw the ball, what happens? What's the equal and opposite reaction? I move backwards. So two things. First of all, why don't I notice that I move backwards if I throw this ball? Okay, so if I was in space, I would move backwards. It would be noticeable. But because I'm on Earth, I've got friction, and friction counteracts that push backwards. That instant where I throw the ball, friction pops up as a static friction, keeps me in place. But the other piece is Newton's third law doesn't talk about actions and reactions. Newton's third law talks about forces and reaction forces. So for every force, there is an equal and opposite. I can't write. If you go out into this, like absolute nowhere of space, the general temperature of space is 3 Kelvin, which equates to, I think it's negative 447 Fahrenheit. Oh, yeah, he froze. 3 degrees Kelvin above it. Oh, yeah, we get there. We were there last Thursday. All right.
Wait, so if you're like coming into Earth, you like blow up, right?
Well, we can talk. There's a lot of things that go on there. So when I threw the ball pushes back on me.
Yeah, that's
So I throw the ball, I push on the ball pushes on me. We saw the same thing in that movie when she threw the fire extinguisher. The fire extinguisher pushed back on her. So we see the same thing. Like if I throw this ball at the ground and the ball strikes the ground, the ball pushes on the ground. The ground also pushes back up on the ball, which is why it bounces. Anytime two objects exert a force on each other, the other force, the other object pushing back on it, also exists. So we could talk about a car crash. When a car smashes into a vehicle, which vehicle is more likely to be in danger of being damaged?
no one that got hit.
Don't go faster.
No, the one that got hit is the one moving.
They're both equally as dangerous to be involved because even though one of them's moving and let's say the other's parked or maybe the other's just moving slowly, any force that this one experiences, that the slower or parked one experiences, it pushes back equally on the one that was moving. So they both experience the exact same amount of force during a collision.
So it's better to be hit in the back because you're in the front.
I mean, that's probably true, depending on the kind of car you're driving.
If you're driving like, okay, let's just say Ford Escape, right?
I don't know what a Ford Escape is. Questions about Newton's third law?